Hello, this is Ilianos. I'm a physics teacher with ATS in Align, and in this video we'll try to solve part 1 from the 2023 AP exam in mechanics. Now, as we scroll down to the exam paper, we see the basic constants and symbols that we need to use with the basic formula and the calculus tips and some geometry rules. So we continue to the first part of the quiz, which is what really matters. We will try to understand what is happening in the diagram. What we see is a spring and an attached object on this, and probably the spring has been compressed. Now, if we really don't understand what's happening on the diagram, we will try to read quickly the question, where I suspect that we will check exactly what we said before, that the spring is compressed, and at some stage we will release the spring and the object will be ejected from this position to a height a little bit above. So a block sitting on a horizontal surface is pushed against a spring. This spring is attached to a wall and it is compressed. The block is released from rest and it slides along the horizontal surface, reaching a height h max. And that's the last sentence is a little bit important, that frictional forces are negligible. So we understand that we will not take friction into consideration. There is no friction in this problem. And a student is making an experiment with a spring P and a spring Q, and he compares the maximum height for the spring P and the maximum height for the spring Q. And for the spring P, there is a force. Now we need to take note that the force for the spring P is 100 times x. The value of k is given right there. And for the spring Q, the force is c times x to the power of 1 over 2. So it is 20 times root of x, or x to the power of 1 over 2. And we see the distribution of the force with respect to the distance, to the compressed distance for the spring. For the experiment, the block is pushed against one of the springs and it is compressed at a distance 0.010 meters. The block is released. In trial 1 we use spring P, in trial 2 we use spring Q, and on the following dots we need to draw and label the forces, so we need to draw a free body diagram for the forces that are exerted on the block the moment that it is released. So each force needs to be represented by an arrow and pointing away from the dot. Basically, we need to follow the rules for the free body diagram. Now, for the two blocks, for sure there will be the force of gravity straight down. The force of gravity, either you will call it with Fg or you will call it with the letter W as weight, and the normal force from the floor, and you will need to make sure that they have equal length, so there is a normal force from the floor. And these two forces for sure are exactly the same for the two objects. Now, regarding the force by the spring, since the spring is compressed, the moment that we release the object, the spring will apply a force to the opposite direction. So there will be a force by the spring to the left in both cases. Now we have to be a little bit careful. Maybe these two forces will be equal, or one of them is a little bit greater. the spring is compressed at a distance 0.01 meters. So if we try to find this value, 0.01 meters is exactly in the middle between 0.0 and 0.02, we can see clearly on the graph that the spring P, which is the bold line, applies a relatively small force, and the spring Q, which is the dotted line, applies a relatively great force. So we'll draw a force to the left for the spring Q, that has a length of 4 blocks. This is the force by the spring, and exactly half of this length, so 2 blocks approximately. So again, this is the force by the spring. And since there is no friction, these are the forces that are applied on the two objects. Again, we have to be a little bit careful about the value of the forces, because this relates to the length of the arrows. Maybe we'll have different masses, so the weight and the normal force will be different. Since we are using the same block, the weight and the normal force here for this application, they are exactly the same, and we can see clearly that the value of the force for spring P is exactly half for the value of the force for spring Q. So from this we get the length of the force by the spring in the case for the spring Q and in the case for the spring P. And we can move on to part 2. What feature or what features, so which properties of the graph 2 could be used to estimate the work done by the work done on the block by its spring? Now, the possible features of the graph in mechanics, there will be either the slope or the area. Now we have to be a little bit careful. Since we're talking here about a work, we need to remember that the basic rule for the work, if we're talking about a constant force, the work is equal force multiplied by distance multiplied by the cosine between the cosine of the angle between the force and the distance. But this rule is only for a constant force. For a non-constant force, there are two ways to find the work, either from the rule integral of force times dx, or in this case, if we have a force versus position graph, then the work is equal to the area under the graph, which is the same as the integration. So we should say that the work is represented by the area under the force, versus position graph. So this is our answer for part B1. And for part B2, there is a compression distance XO, for which the maximum height reached by the block is the same regardless of the spring. And we need to figure out if this value of XO is greater, less, or equal than 0.04 meters. Now, usually, if we have a part B1 and a part B2, or sometimes even for part A and part B, these parts are related to each other. And in this case, probably the part B2 will somehow be related to part B1. So the given is that the two different springs, the spring P and the spring Q, if they are compressed at a certain distance, then the object will reach a certain height. And for this, we need to figure out if the compressed distance is more or less or equal to 0.04 meters. And the only given that we have is the force versus position graph. And a little bit careful, if we check what is happening at 0.040 meters, we see that the spring applies the same force. And maybe some students from this, they will understand that since the force is the same, maybe the distance, the height that the object will be ejected will be the same. But we need to understand what are the factors that affect this height. So when the spring is squeezed and then we release it, the spring provides energy. The spring provides energy, in this case this is potential energy of the spring, that it is transformed into kinetic energy on the object, and as the object is moving upwards on the inclined plane, this kinetic energy decreases and it is converted to potential energy. And at the top there is a potential energy that it is mass times g times height, and this height depends on the energy by the spring. And the energy by the spring is the work by the spring. So the height depends on the work by the spring, which is the area under the graph. So since the height depends on the work, then we need to figure out if the work for the two springs will be the same at a distance more, less or equal to 0.040 meters. And definitely it's not the same at 0.040 meters because we have a relatively big value for work for the spring Q, because the area under the graph is slightly greater than the area under the graph by spring P. So we need to figure out at what distance these two areas will be approximately equal, and this will definitely be at a distance, we don't know exactly where, but it will be at a distance greater than 0.040. So at some point here, the area under the bold graph for P and the area under the dotted graph for Q, they will become approximately equal. So I suspect that this will be approximately at 0.060 meters. So we need to say that this distance XO is definitely greater than 0.040 meters. And the justification, we use the graph in figure 2, we need to say that the potential energy by the spring is converted to kinetic energy on the block, and potential energy as the block moves up on the inclined plane. Now in this case, instead of the potential energy by the spring, we would say the work by the spring, just to relate it with part B1. The work done by the spring on the block is converted to kinetic energy and then to potential energy. So the height depends on the work, and the work is equal to the area under the graph, which is equal to the work under the graph. So we need to say for equal works, we need to have equal heights, or for equal areas, we need to have equal heights. And I made a mistake, I wrote to the work under the graph, I should have written to the area under the graph. So at XO greater than 0.040, the area under the two graphs is equal. The areas under the two graphs are equal. or a sentence that makes sure that relates the work or the energy to the potential energy and the height, and this work is related to the area under these graphs. So we need to make sure that we mention these keywords. We can move on to part B3. On the axis provided for spring P and spring Q, we need to draw the graph for the maximum height that it is reached with respect to the compressed distance by the spring. Now, we will work for the first spring. We said that the work eventually will become potential energy. So the work by the spring, the work by the linear spring, let's say the spring P, which is the potential energy of the spring, 1 over 2 kx squared, will become potential energy on the object, which is mass times g times height. So the height depends on the compression to the power of 2. So there is a quadratic relation between the height and the compression of the spring. So there will be a curve that will resemble a parabola, approximately like this. Now, we don't need to calculate the values, but we need to show the curve, that it is a parabola. Now, for the second spring, for the non-linear spring, for the spring Q, the force by the spring is 20 times x to the power of 1 over 2. So the work by the spring, the work will be integral of force times dx. So integral of 20 times x to the power of 1 over 2 dx. And this is 20 times, we need to increase the value of the power by 1, so 1 over 2 plus 1 is 3 over 2, divided by the new power, which is 1 over 2. So 20 over 1 over 2 is 40, x to the power of 3 over 2. So the same work will be 40 x to the power of 3 over 2. And again, the height will depend on the compression to the power of 3 over 2. So again, it is a curve. It's a curve that will look approximately like a parabola. If I'm not mistaken, for the spring Q, it will turn the power 3 over 2. It resembles a parabola that has a faster way of going up. However, sorry for that, let me change it. If we check the graph, the area under part Q eventually will be less than the area under the graph of part P. So since there is less area, it means that there is less work. And since there is less work, it means that there is less energy. And this will bring a smaller value for the height. So the value of the height the value of the final height for the same compression will be less. However, for the very, very start, the area of the spring Q is slightly bigger, slightly greater than the area of the spring P. This means that the spring Q initially provides more energy, and since it provides more energy, it can result in a greater height. So for relatively small distances, for relatively small compressions, it will provide a greater height. So we need to make sure that we show this on the graph. So both graphs will be curves. Maybe I should increase a little bit the height for the first one so that we can show the curve for the second one a little bit more. So we have the spring P and the spring Q and the relationship for the height that they can provide for certain displacements. And this agrees with the conclusion that we had on part B2, that for a certain distance, that it is more than 0.4, greater than 0.4, the two springs, the compression on the two springs will result on the same height. So we can remove this is not really necessary, but we need to make sure that we show this part, that for initial compressions that are in the region between 0 and 0.6, the spring Q results in a greater height, somehow like this. And also all of this is not really necessary. And we move on to part C. Well, now the spring Q is attached to the wall. Again, we need to remember the value for the force on spring Q, which was 20 times x to the power of 1 over 2. A mass, a block A of mass 0.12 kgs and the block B are at the positions that we see. The block A is held at rest, so here the velocity is 0. And the student releases the block A, it moves down the ramp, okay. Eventually there will be a collision. We know the height of A, that is 0.75, and this is very, very important. After the collision, the two blocks stick together and move to the right and compress the spring. There is no friction, and we need to figure out what is the velocity of the two blocks immediately after the collision. So this block A will speed up. It will come to the base of the inclined plane and will collide with block B, and we need to find what will be the velocity of these two objects that are stick together right after the collision, and later we need to find what is the maximum compression of the spring. Now, eventually we'll use the law of conservation of momentum in order to find the velocity for part C1, but in order to use the law of conservation of momentum, we need to find the velocity of the spring, the velocity of the block A at the moment before the collision. So just before the collision, or when it is on the base of the inclined plane. So there is a mechanical energy at the top and there is a mechanical energy at the bottom. So we can use the law of conservation of mechanical energy between the top and the bottom. This is not the only tool that we can use. We can use, for example, the work energy theorem. The mechanical energy at the top is kinetic energy plus potential energy top and top, and the same thing, kinetic energy bottom plus potential energy bottom. Now, the kinetic energy at the top is 0 because this object A is at rest, and the potential energy at the bottom is 0 because the height is 0. So the mass times g times height is equal to 1 over 2, the mass of object A times velocity just before the collision to the power of 2. I will need to bring a calculator for this, I believe. The mass is cancelled, and if we place the values for g, which is 9.8, the height that I believe it is given 0.75, and we multiply by 2 to cancel the 1 over 2, we'll get v squared, and from this we bring times 9.8 and then root it. We bring that the value for the velocity of object A just before the collision is approximately 3.8 meter per second. However, we don't need to calculate this. This is not our final answer. We need to figure out what is the velocity of the two block system right after the collision. So these two blocks, one of them is moving with 3.8 meters per second for block A, and block B that it is at rest, so it doesn't have velocity. They stick together and move with the velocity after the collision. So we can use the law of conservation of linear momentum. So the momentum before is equal to the momentum after. So the mass of object A times the velocity of object A plus the mass of object B times the velocity of object B is equal to the combined masses, because they stick together, mass A plus B together, times the velocity of the combined object just after the collision. Now, the first mass is 0.120. The velocity we found it 3.8. In reality it was 3.83. We will replace that value in the calculations. The velocity of object B was 0, and the mass A plus the mass B together are 0.19 times the velocity that it is unknown. So after the calculations and divide by 0.19, we bring that the velocity of the two objects together is approximately 2.42 meters per second, which is our final answer. And after this, we need to find the maximum compression of the spring. So what will happen is that one object that has a mass of 1.9 kilograms, 0.19 kilograms, is moving with a velocity of 2.42 meters per second, and it is about to collide with a spring that it is fixed on a wall. Obviously, right after the collision, this spring will be compressed. This is what we need to find, the compressed distance. And the maximum compression for the spring happens when the velocity of the objects becomes 0. So the object that it is moving loses kinetic energy, and this kinetic energy becomes potential energy on the spring. So again, we can use the law of conservation of mechanical energy. Mechanical energy before is equal to mechanical energy after. So the kinetic energy of the two objects before plus the potential energy of the spring before the collision is equal to the kinetic energy after plus potential energy after. Now, right after the collision, the two objects are, not right after, but at the maximum compression, the velocity of the two objects is 0, so there is no kinetic energy. And before the collision, the potential energy of the spring was 0 because it wasn't compressed. So the kinetic energy of the two objects was 1 over 2 times mass, which is 0.19, times the velocity, that it is 2.42 to the power of 2. And the potential energy of the spring, now usually for a linear spring, the potential energy is 1 over 2 kx squared. But if I remember correctly, this is not the linear spring. Exactly, this is the spring Q. And we said that the spring Q has a force that it is 20 times x to the power of 1 over 2. So the potential energy, now in reality the potential energy is equal to the work by the spring, and we had calculated the work by the spring. I erased it, if I remember correctly, it was 40x to the power of 3 over 2, but we can calculate it again. It is integration of f times dx. The value for this, in reality the potential energy has a negative in front of the integral, but the value for the potential energy, the absolute value, is f times dx, so integral of 20x to the power of 1 over 2 dx, so it is 20 times x to the power of 3 over 2 divided by 3 over 2. I believe that we made a mistake in the previous part. I think I wrote 1 over 2, but it doesn't change our conclusions. So it will become 40 over 3 x to the power of 3 over 2. And we need to solve this equation for x. Let me erase all of this. We don't need it anymore. So let's start with the first part. So 2.42 to the power of 2 times 0.19 times 1 over 2. So 0.55. is equal to 40 over 3, so 13.33, times x to the power of 3 over 2. Now either we'll bring this equation to solver, or the first thing that we can do is square everything. Actually I should have divided first by 13.3, so let me do this thing first. 0.557 divided by this brings 0.04 is equal x to the power of 3 over 2. Then we square it, we square this and we can square that, so to the power of 2 this is 1.75 times 10 to the power of negative 3 is equal x to the power of 3, and then we need to apply cubic root. So we find that the maximum compression is approximately 0.12 meters, which is our final answer. And we continue to part D, where we have the spring Q. Let me just write what we know for the spring Q. It was this, or he calls it force by the spring Q is equal C to the power of x of 1 over 2. And it is replaced by a new spring, a spring R with a similar force. The force for the spring R is D times x to the power of 1 over 2, so the coefficient in front of the variable x is different. And the maximum compression by spring R is greater, actually this is a given, the maximum compression by the spring R is greater than the maximum compression by the spring Q, and we need to figure out which coefficient is greater, C or D. Now we need to bring the previous solution here, that the mechanical energy before doesn't change, so it is a constant number, is equal to the potential energy by the spring, and the potential energy by the spring, if we remember, it was integration of F times dx, so it is the coefficient of, now we'll call it the coefficient C times x to the power of 1 over 2, and this was C to the power of 3 over 2 divided by 3 over 2, so C x to the power of 3 over 2 divided by 3 over 2, so multiplied by 2C over 3. Now, the coefficient, actually, it is a variable, so I will not call it with the letter C, just in order to confuse, I will say the coefficient, let's say it's A. Now, we know for a fact that the maximum compression for R is greater than the maximum compression for Q. So, the value for R is a great value, and the mechanical energy is constant. The only way that this can happen is that the coefficient in front of the variable is smaller. So what we can say is that the mechanical energy is equal with 2. Now, in the case for spring Q, it will be C to the power of C x to the power of 3 over 2 divided by 3, and the same mechanical energy, it will be 2 d x to the power of 3 over 2 divided by 3. But we know for a fact that the x of R, the x of the spring R, is greater than the x of the spring Q. We don't need this anymore. And the mechanical energy is the same mechanical energy, so 2C times x of Q to the power of 3 over 2 divided by 3 will be equal to 2 over 3 dx of R to the power of 3 over 2. The 2 and the 3 are cancelled, and we can say that x of R divided by x of Q to the power of 3 over 2, it will be C over D. Now, since the x of R is greater than the x of Q, this is the given, the only way that this can happen is that the C is greater than D. So we need to mention that the mechanical energy is the same for the two objects, for both cases, and we need to mention that this mechanical energy is equal to the potential energy by the spring, and this potential energy by the spring is, for the first spring, 2 over 3 Cx for Q to the power of 3 over 2, and it is equal to 2 over 3 dx of r to the power again of 3 over 2, and this is a complete justification. I think this is the last part, yes, before we go to question 2. We will solve question 2 on the next video. I hope you enjoyed the solution. If you have any comments, feel free to comment on this page. I hope that you find it productive studying for all your subjects, and especially the most important subject of them all, which is physics. Thank you for watching. Have a good time.